There are places on this planet where light never reaches, where water pressure is so extreme it crushes any structure human beings have managed to build, where temperatures drop to just above freezing and stay there, never quite crossing that threshold. The deep ocean is not simply water, it is another world. A world humanity has explored less than the surface of the moon, and one that holds within it a particular acoustics nearly perfect, capable of carrying sound across distances that defy intuition. In that world, somewhere in the South Pacific, in the summer of 1997, something produced a sound, not an ordinary sound. It was a signal of unusual intensity, with characteristics that matched no previously cataloged phenomenon. It was picked up by sensors separated from each other by thousands of kilometers, and for years no one knew with certainty what had produced it. That sound has a name. They call it the bloop. To understand what happened in 1997, you first need to understand how the ocean listens. The National Oceanic and Atmospheric Administration, the NOAA, has operated since the 1990s a network of hydrophones distributed across the world's oceans. A hydrophone is, in simple terms, a microphone designed to function underwater. But the ones used by NOAA are built to capture sounds at very low infrasonic frequencies that the human ear cannot directly perceive, and to do so across enormous distances. That is possible because of a physical phenomenon that occurs in the ocean at certain depths. There is a layer of water generally located between 600 and 1,200 meters down, where temperature and pressure create conditions that trap sound and channel it horizontally with minimal energy loss. Scientists call it SOFAR, the sound fixing and ranging channel. It is in practical terms an acoustic highway. A sound produced within that channel can travel thousands of kilometers without dispersing. During the Cold War, several navies used this principle to detect submarines. When the conflict ended, part of that infrastructure was repurposed for scientific use, and NOAA began using it to study underwater earthquakes, volcanic eruptions, movements of ice, and the activity of marine animals. On May 19, 1997, at 13 hours and 27 minutes Universal Time, several hydrophones across the South Pacific simultaneously detected a signal of great intensity. The sound lasted approximately 1 minute. Its frequency was extremely low, which allowed it to travel long distances within the SOFAR channel, and that is exactly what it did. The sensors that detected it were separated by several thousand kilometers. Triangulation placed the origin somewhere in the South Pacific, near 50 degrees south latitude and 100 degrees west longitude, international waters far from any inhabited coast. What stopped the analysts was the profile of the signal. It had a rapid rise toward higher frequencies, a pattern described as an upsweep. It was not the profile of an earthquake, nor of an underwater explosion, nor of any known animal. When the sound was sped up to make it audible to the human ear, some researchers described something resembling a deep, distorted gurgling. That is where the informal name came from, the one that eventually made its way into the scientific vocabulary of the field. What drew the most attention was the intensity. The bloop was powerful enough to be detected by multiple stations separated by thousands of kilometers. To accomplish that, even within the SOFAR channel, its source had to be extraordinarily powerful. Estimates suggested it clearly exceeded any recorded call from marine animals, including blue whales, the largest animals known to science and among the most powerful biological sound producers on the planet. That opened the first major question. If no known animal could produce a sound of that intensity, what had produced it? In the years that followed, researchers considered several hypotheses grounded in documented natural phenomena. Submarine seismic activity was the first to be evaluated. The floor of the South Pacific is not geologically stable, and an earthquake or a rupture in the seabed can produce acoustic signals that travel through the SOFAR channel. However, the profile of the bloop did not match the typical patterns of seismic activity. Submarine volcanic processes were also considered, with the same result: insufficient correlation. The hypothesis that gained the most support over time involved ice. The South Pacific is adjacent to Antarctica, a region where enormous masses of glacial ice fracture continuously. When a glacier breaks apart or an iceberg collapses, the process generates acoustic signals that can be extraordinarily intense, with frequency profiles that vary depending on the nature of the movement. NOAA researchers found a significant correspondence between the profile of the bloop and the type of signals generated by sea ice activity. The technical argument is precise. When a large mass of ice fractures abruptly, it first produces the lowest frequencies, and then, as the fracture propagates, the frequencies rise. That ascending sweep is exactly the profile that defines the bloop. The duration of approximately 1 minute is also consistent with that type of event. In 2012, researchers who had studied Antarctic acoustics in depth published analyses that reinforced this interpretation. The zone of origin estimated by triangulation is geographically consistent with the presence of large icebergs. Even so, the case is not fully closed. The cryogenic hypothesis is the most solid available, but there are elements that have not been explained with complete precision. The first is intensity. Even if the source was a glacial event, the power recorded exceeds what previous documentation of similar phenomena had shown. No specific event has been identified on that date and in that location to serve as a direct match. The second is the singularity of the event. The bloop was never detected again. The absence of repetitions does not invalidate the hypothesis, but it leaves an open space. The third is geographic imprecision. Triangulation narrows down a zone, not an exact point, and no expedition was ever mounted to the region to verify direct evidence. Those elements are not enough to discard the dominant explanation, but they are enough to maintain that the phenomenon has not been explained with the precision science requires to formally close it. The oceans produce sounds constantly. Many were never cataloged before the monitoring infrastructure that NOAA developed over recent decades existed. The network that detected the bloop has since captured dozens of anomalous signals, some identified with precision, others still under analysis. Progress has been real, but the deep ocean remains an environment with far less data density than other natural systems science studies. What the bloop illustrates is not the existence of something impossible to explain. It illustrates the actual state of human knowledge about one of the most vast and least accessible environments on the planet. The deep ocean is not a mystery because it holds impossible secrets. It is a mystery because the tools have not yet been built, the data has not yet been gathered, and the resources have not yet been directed toward understanding it with the depth it deserves. In 1997, something produced a sound in the depths of the South Pacific. It reached sensors distributed thousands of kilometers away. It lasted approximately 1 minute, and then it never came back. Science has a probable answer. It does not have a definitive one. That, for now, is all there is.